Here, I want to discuss one common type of problem where integration comes up: finding the average of a continuous variable. This is a perfectly useful thing to know in its own right, but what's really neat is that it can give us a completely different perspective for why integrals and derivatives are inverses of each other. To start, take a look at the graph of sine of x between 0 and pi, which is half of its period. What is the average height of this graph on that interval? It's not a useless question. All sorts of cyclic phenomena in the world are modeled using sine waves. For example, the number of hours that the sun is up per day, as a function of what day of the year it is, follows a sine wave pattern. So if you wanted to predict, say, the average effectiveness of solar panels in summer months versus winter months, you'd want to be able to answer a question like this: what is the average value of that sine function over half of its period? Whereas a case like this is going to have all sorts of constants mucking up the function, you and I are just going to focus on a pure, unencumbered sine of x function. But the substance of the approach would be totally the same in any other application. It's kind of a weird question to think about though, isn't it? The average of a continuous variable. Usually with averages we think of a finite number of variables, where you can add them all up and divide that sum by how many there are. But there are infinitely many values of sine of x between 0 and pi, and it's not like we can just add up all of those numbers and divide by infinity. Now, this sensation actually comes up a lot in math, and it's worth remembering, where you have this vague sense that what you want to do is add together infinitely many values associated with a continuum, even though that doesn't really make sense. And almost always, when you get that sense, the key is going to be to use an integral somehow. And to think through exactly how, a good first step is usually to just approximate your situation with some kind of finite sum. In this case, imagine sampling a finite number of points evenly spaced along this range. Since it's a finite sample, you can find the average by just adding up all of the heights sine of x at each one of these, and then dividing that sum by the number of points that you sampled, right? And presumably, if the idea of an average height among all infinitely many points is going to make any sense at all, the more points we sample, which would involve adding up more and more heights, the closer the average of that sample should be to the actual average of the continuous variable. And this should feel at least somewhat related to taking an integral of sine of x between 0 and pi, even if it might not be exactly clear how the two ideas match up. For that integral, remember, you also think of a sample of inputs on this continuum, but instead of adding the height, sine of x at each one, and dividing by how many there are, you add up sine of x times dx, where dx is the spacing between the samples. That is, you're adding up little areas, not heights. And technically, the integral is not quite this sum. It's whatever that sum approaches as dx approaches 0. But it is actually quite helpful to reason with respect to one of these finite iterations, where we're looking at a concrete size for dx and some specific number of rectangles. So what you want to do here is reframe this expression for the average, this sum of the heights divided by the number of sampled points, in terms of dx, the spacing between samples. And now, if I tell you that the spacing between these points is, say, 0.1, and you know that they range from 0 to pi, can you tell me how many there are? Well, you can take the length of that interval, pi, and divide it by the length of the space between each sample. If it doesn't go in perfectly evenly, you would have to round down to the nearest integer, but as an approximation, this is completely fine. So if we write that spacing between samples as dx, the number of samples is pi divided by dx. And when we substitute that into our expression up here, you can rearrange it, putting that dx up top and distributing it into the sum. But think about what it means to distribute that dx up top. It means that the terms you're adding up will look like sine of x times dx for the various inputs x that you're sampling. So that numerator looks exactly like an integral expression. And so for larger and larger samples of points, this average will approach the actual integral of sine of x between 0 and pi, all divided by the length of that interval, pi. In other words, the average height of this graph is this area divided by its width. On an intuitive level, and just thinking in terms of units, that feels pretty reasonable, doesn't it? Area divided by width gives you an average height. So, with this expression in hand, let's actually solve it. As we saw last video, to compute an integral, you need to find an antiderivative of the function inside the integral, some other function whose derivative is sine of x. And if you're comfortable with derivatives of trig functions, you know that the derivative of cosine is negative sine. So if you just negate that, negative cosine is the function we want, the antiderivative of sine. And to gut check yourself on that, look at this graph of negative cosine. At 0, the slope is 0. And then it increases up to some maximum slope at pi halves, and then goes back down to 0 at pi. And in general, its slope does indeed seem to match the height of the sine graph at every point. So what do we have to do to evaluate the integral of sine between 0 and pi? Well, we evaluate this antiderivative at the upper bound and subtract off its value at the lower bound. More visually, that is the difference in the height of this negative cosine graph above pi and its height at 0. And as you can see, that change in height is exactly 2. That's kind of interesting, isn't it? That the area under this sine graph turns out to be exactly 2. So the answer to our average height problem, this integral divided by the width of the region, evidently turns out to be 2 divided by pi, which is around 0.64. I promised at the start that this question of finding the average of a function offers an alternate perspective on why integrals and derivatives are inverses of each other, why the area under one graph has anything to do with the slope of another graph. Notice how finding this average value, 2 divided by pi, came down to looking at the change in the antiderivative, negative cosine x, over the input range, divided by the length of that range. And another way to think about that fraction is as the rise over run slope between the point of the antiderivative graph below 0 and the point of that graph above pi. And now think about why it might make sense that this slope would represent an average value of sine of x on that region. Well, by definition, sine of x is the derivative of this antiderivative graph. It gives us the slope of negative cosine at every point. So another way to think about the average value of sine of x is as the average slope over all tangent lines here between 0 and pi. And when you view things like that, doesn't it make a lot of sense that the average slope of a graph over all of its points in a certain range should equal the total slope between the start and end points? To digest this idea, it helps to think about what it looks like for a general function. For any function, f of x, if you want to find its average value on some interval, say between a and b, what you do is take the integral of f on that interval divided by the width of that interval, b minus a. You can think of this as the area under the graph divided by its width, or more accurately, it is the signed area of that graph, since any area below the x-axis is counted as negative. And it's worth taking a moment to remember what this area has to do with the usual notion of a finite average, where you add up many numbers and divide by how many there are. When you take some sample of points spaced out by dx, the number of samples is about equal to the length of the interval divided by dx. So if you add up the values of f of x at each sample and divide by the total number of samples, it's the same as adding up the product f of x times dx and dividing by the width of the entire interval. The only difference between that and the integral is that the integral asks what happens as dx approaches 0. But that just corresponds with samples of more and more points that approximate the true average increasingly well. Now, for any integral, evaluating it comes down to finding an antiderivative of f of x, commonly denoted capital F of x. What we want is the change to this antiderivative between a and b, capital F of b minus capital F of a, which you can think of as the change in height of this new graph between the two bounds. I've conveniently chosen an antiderivative that passes through 0 at the lower bound here, but keep in mind, you can freely shift this up and down, adding whatever constant you want to it, and it would still be a valid antiderivative. So the solution to the average problem is the change in the height of this new graph divided by the change to the x value between a and b. In other words, it is the slope of the antiderivative graph between the two endpoints. And again, when you stop to think about it, that should make a lot of sense, because little f of x gives us the slope of the tangent line to this graph at each point. After all, it is by definition the derivative of capital F. So, why are antiderivatives the key to solving integrals? Well, my favorite intuition is still the one that I showed last video, but a second perspective is that when you reframe the question of finding an average of a continuous value as instead finding the average slope of a bunch of tangent lines, it lets you see the answer just by comparing endpoints, rather than having to actually tally up all of the points in between. In the last video, I described a sensation that should bring integrals to your mind. Namely, if you feel like the problem you're solving could be approximated by breaking it up somehow and adding up a large number of small things. And here, I want you to come away recognizing a second sensation that should also bring integrals to your mind. If ever there's some idea that you understand in a finite context, and which involves adding up multiple values, like taking the average of a bunch of numbers, and if you want to generalize that idea to apply to an infinite continuous range of values, try seeing if you can phrase things in terms of an integral. It's a feeling that comes up all the time, especially in probability, and it's definitely